So this seminar will make you understand in a qualitative way three important jet streams, why they are there and why they look as they do. And to start, I want to point out this very common illustration. You find it in many textbooks and in many more places over the web. And it's an example of whether mathematics is correct, but the interpretation is crucially wrong. The mathematics show the acceleration of an air parcel in a constant pressure gradient. So the equations are quite right. The image conveys a feeling of an air parcel acting like a well-behaved motorist entering the motorway and attaining the agreed geostrophic speed. It all looks very nice, but it's actually wrong and crucially wrong. And I will show you why. Because as a mathematics to the left wants to tell us something else happens. It actually is not a well-behaved motorist, it's more like road rage, as it's called in England. The car is oscillating from left to right and is rather wild and even is going double the sort of agreed geostrophic speed. And just because it becomes super geostrophic, the Coriolis force to the right becomes stronger than the pressure gradient force, so the air is moving back to the right, and then when it goes down to zero, the whole thing starts over again. And this looks very much like playing with mathematics, but it's not. It's actually partly what actually happens in the atmosphere, and partly gives an entrance key to understanding some important jet streams. So the three important jet streams are the nocturnal jet stream, the synoptic scale jet stream, and the subtropical jet stream. The nocturnal jet stream is perhaps the least known. It is quite dangerous. It happens in the night. During the day can be normal winds, but when the sun sets and there is a cooling of the ground, an inversion is formed at the bottom of the atmosphere, and suddenly the wind at higher levels are decoupled from the Earth's surface, and the frictional effect is lost. And now the wind comes into an acceleration which might reach 2 or 3 times the wind speed it had during the day. And I will show you this in more detail with vector algebra. So here we have a pressure gradient force, and we have a wind, and these two have an acceleration, but if the wind is now in the friction layer, there is also friction which balances this acceleration, so the wind is steady. It's balanced by 3 forces. So this is what we experience during daytime. But then let's now introduce the geostrophic wind, because this wind is not geostrophic because of the friction. So here we have now the geostrophic wind, and there's a difference between the geostrophic wind and the real wind, and we call that V minus Vg. Now the very interesting thing with this is that there is now this acceleration which I talked about previously is actually mathematically a rather beautiful consequence of the adiastrophic wind, the V minus Vg. It's called the adiastrophic wind component. So, and because of the mathematics, this is a cross product, it tells us that this acceleration is perpendicular to the adiastrophic component. Now all this sounds very mathematical, but the consequence again is interesting. It means that now the wind, the peak of the wind is going into a circle. And all this is very beautiful, and famous British mathematician Sutcliffe once called this equation the heart of dynamic metrology. And I agree with him, it's quite simple, but it has a rich potential of interpretations. So let's see now what happens in the mathematics and compare with observations. So now this acceleration is moving the wind in a circle. Now we can see the first effect, how the wind is increasing. And this is what's happening in the nocturnal jet during the night. The wind is increasing. And it's increasing at most slightly later when this wind is actually parallel to the geostrophic wind. So here you have super geostrophic winds in this part of the circle. Then it goes round, and a typical period of the inertial circle is 15 hours, 12, 15, 16 hours on our latitudes. So then when it's here, it's time for the sun to come back, and the whole process might be interrupted. But mathematically, now we come into the phase where the winds are subgeostrophic. They are weaker than the geostrophic wind. And all this can be easily verified, and meteorologists in the Netherlands, in Holland, are quite interested in these nocturnal jets because they can bring in pollution from Belgium, from Germany, rapidly into Holland. So there's a lot of studies in the Netherlands on nocturnal jet streams. And here is an example where this is a theoretical wind changes. So the wind vectors move along this, the peak moves along this circle, theoretically, and this is how the wind actually varied on this particular day in Holland. As you can see, from a daytime speed of 6 to 7 meters per second, the wind increased to almost gale force, 13 to 14 meters per second, at a short period during the night. Then we come to synoptic jet streams, the ones that the polar front jet stream, for example. And again, we start with this mathematical play, so to say. What can that teach us? Now things became a bit complicated graphically. I would like to have been in company with Walt Disney and all his wonderful images. But now, whereas the nocturnal jet stream is a rather short-lived jet stream, these polar front jet streams have larger sizes and live longer. So now what is not timed to happen with the nocturnal jet stream happens with a large-scale jet stream, namely a mutual adjustment between wind and pressure. Here the wind and pressure are not in any balance. But if you allow in time, the wind will adjust to the pressure and the pressure will adjust to the wind. And when that happens, this supergeostrophic will be dampened. So here is my attempt to show how the pressure adjusts towards the wind and the wind adjusts towards the pressure. That weakens the supergeostrophic winds. They are still strong, but they are weakened. And when the wind was zero, they now become have values above zero. So what you have is a dampening of this rather extreme road rage trajectory into a smooth and also extended curved path of the wind. And this is what you can see in unperturbed jet streams, how they look like sort of upside down bananas, and a reflection of their first mathematical shape, which is actually a cycloid. A cycloid was the first one, and now it is also a cycloid, but a dampened cycloid. So we can now understand why the jet streams, unperturbed, have this shape. Then we come to the subtropical jet stream, and then there is a a long-standing problem in meteorology. People have tried to understand the subtropical jet stream by applying the law of conservation of angular momentum. Angular momentum is what you apply to understand the spinning up of a ballerina or an ice skater. He or she will spin faster when he contracts his arms. And this is appealing to apply to the atmosphere, where you also have some sort of convergence of winds coming from the tropics up to higher latitudes. But when you do that, for example, moving a ring of air from the equator to 30 north, following the law of angular momentum gives winds of 134 meters per second, which is 2 or 3 times more than is observed. And there have been all kinds of discussions over 100 years how to explain this. But in my view, it's actually a misunderstanding, and I will come back to the root of the misunderstanding. And before that, come back to this picture here, and with the addition now that we assume that the isobars are from east to west, are parallel to the latitudes. We did not do that before, but now we say that these isobars are from east to west along the latitudes. We still have this increase of the wind. So here is the north-south. And now what can we learn from this? Well, leaving angular momentum for a brief moment aside, acceleration in constant pressure fields have been calculated. Among them, there was a paper more than 60 years ago by an Australian meteorologist, Adrian Gordon, and his colleague Shaw. They calculated these trajectories in constant pressure gradients in the tropics. And I will come back to this diagram of theirs. So they show how it's accelerating from different latitudes, from 10 south, from the equator, and from 10 north. And very much, as you saw, being affected by the Coriolis effect and moving eastward. I will come back to this diagram later on. But it's a very important results, because if now the pressure gradient force is accelerating and the isobars are parallel to the latitudes, it means that the pressure gradient force is perpendicular to the east-west latitudes. And that means that this force has no effect on the angular momentum, only a force that has a component parallel to the latitudes in east-west direction will increase or decrease angular momentum. But this force, this direction, will not affect the angular momentum. So for these motions, also angular momentum is conserved. And that has very important consequences. So now we apply Gordon's calculations, knowing that they also conserve angular momentum, which is not mentioned in Gordon's paper. So here we have now the wind accelerated as before in a constant pressure field, and the winds are very high. But now we can understand that these high winds are consistent with the momentum, excessive winds. So we now have a physical understanding of why the winds are so strong. And it means also that we understand now why they in reality are not so strong. It's because, for the same reason as I showed before, these excessive winds, double the geostrophic winds, are dampened by the mutual adjustment between pressure and wind. So what we have now is, as a result, a subtropical jet stream with slightly higher winds, slightly supergeostrophic winds in the crests, in the crest here, and slightly subgeostrophic in the troughs. So there is no mystery anymore. We know why the winds become so strong. We know what then is dampening. It's a normal geostrophic adjustment. So there's no need to involve friction or turbulence or whatever that has been suggested over the years. So this is now the subtropical jet stream. And now back to Gordon's calculations. When he started his calculation, and this is now in a constant pressure gradient. So when he started his calculations from the equator, the air moved first rather straight northward because the Coriolis effect is weak, but then with increase in latitude, the Coriolis force became stronger and stronger and deflected the wind more strongly eastward. Here he starts from 5 degrees north, and more or less now it is more quickly deflected to the east because the Coriolis force is slightly stronger. And then this is also the typical outflow region in summertime when the Hadley cell is displaced north of the equator. And here is a typical outflow in wintertime of the Hadley cell when it's south of the equator. And as you can see, they, in the end, more or less end up at the same latitude. But the one from the summer is much weaker than one from the winter. You can also see that the reason is that for a rather long time there is no real deflection, so the air is just accelerated without being deflected. But here it's fairly early deflected, so it has not much time to accelerate. And then, and by the way, in this part the Coriolis effect is weak, but the beta effect, which I will come back to, is strong. So the beta effect is a cosine dependence of the change of the Coriolis effect. Now we have his calculations from 10 degrees north. It's again a summer scenario, and the wind has not much time to accelerate, so it only gets up to 51 meters per second. On the other hand, when you start from the winter position of -10 or 10 degrees south, there is a lot of time to accelerate, and now the wind speed is up to 90 meters per second. But in spite of the start over a range of 20 latitude degrees, still they more or less end up in a rather narrow zone about 5-7 latitude degrees. So independent, more or less independent on where the air starts, they will end up in the same position but with different speeds. And so here is a summary of these results. In summer we have the outflow from the Hadley cell north of the equator, less time to accelerate, and the winds are weaker. Here we have in winter time, it starts south of the equator, long time to accelerate, and the winds can be quite substantial. Now this is now for constant pressure gradients, but of course there will be an adjustment between wind and pressure. And a paper by Chester Newton from 1959 suggests a simple thumb rule that the wind after adjustment will be about half of the value it has without any adjustment. So applying that thumb rule, we will have in summertime around 30 north, winds of 20-30 meters per second, which does not really constitute a jet stream. That is why we don't have a subtropical jet stream on the summer hemisphere. However, in the winter hemisphere, the wind would be typically 40-50 meters per second, which agrees fairly well with the observed values of the subtropical jet stream. So this gives a qualitatively explanation to why we have a subtropical jet stream, about its strength, and why we don't have any subtropical jet stream in the summer hemisphere. We can also apply this reasoning again in another way to understand why we have strong winds on Venus at high latitudes, and also on Jupiter and Saturn, why they are at very low latitudes, almost at the equator, and relatively weak. So these are three examples where the correct interpretation of the mathematics leads into insights into three different types of jet stream, something that is impossible if you make the incorrect interpretation of the equations. Finally, why has there been confusion about the angular momentum? And the reason, in my view, is that moving the air from the equator to, for example, 30 north, and angular momentum is conserved. The advantage of conservation principles is that you don't have to think deeply about what is happening between A and B during this process. But actually one should do that. Is this motion possible, or under what conditions is this motion taking place? And there are two ways you can transport air from the equator to the, for example, 30 north. And one would be, as I showed, by accelerating in a pressure gradient. Then you saw the results. But what has been implicitly and not quite realized by people who have been doing this over the last 100, 150 years is that they have applied an impulsive motion. So they even said pushing or impulsive motion of the air from the equator to 30 north. And then actually the wind is not starting from zero, as in my case, where you accelerate. The wind has to actually be pushed by 134 meters per second to even reach the desired latitude of 30 degrees. There it is because it's affected by the Coriolis effect. There is no change of the wind. So the wind has just kept its velocity but changed its direction from pointing north to pointing east. And then when it has reached 30 north, it will of course be supergeostrophic and go back to, not supergeostrophic, it will, following an inertia circulation, just turn back to the equator. Now this is all mathematically correct, but as everybody can understand, it applies for some other mechanical system than the Earth or a rotating planet. So the whole approach is wrong from the start. You cannot use impulsive motion when angular momentum is conserved, fine, but it does not apply to geophysical problems. Thank you. So how many